Okay, it's time for our afternoon session. I'm Mike Simmons. I guess everyone knows that because I just spoke before lunch. And I'll be chairing this session. We have 4 talks for this session. First one will be Rita Guerra, speaking on the diagnosis of misconceptions in basic astronomy, something that we all have to deal with, I think.
Hello everyone, I am starting to present myself. My name is Ana Rita Guerra. I'm a teacher, a Portuguese teacher of physics and chemistry. I did this work on my master that I did after the Bologna process. And first of all, before I start to explain all that we have done, I'm going to show you a short movie. You can see the full version on YouTube. It's from the 90s, but it's not so updated as we think.
Candidate in art.
Despite a lifetime of the very best education, students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happens because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get farther away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse, even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons. We carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
So, I decided to construct a diagnostic test. So this test aims to be a tool to expose mental models of students and serve as a starting point of the discussion of this phenomena. We took account of the sample size and the type of study, and it was found the desirability of making a test consider their advantages and disadvantages. I reviewed the international literature. I took all the misconceptions between 12 and 16 years old, and I took also most of the items of some of the categories that I'm going to show you next. So, after the identification of major categories for items, a selection of these items was adapted to Portuguese curriculum and validate. The items that I choose was essentially items with images. So those images, special care was taken with the quality and clarity of those images, and we changed it. So we have 7 categories: planet Earth in space, orbits and astronomical objects, phases of the moon, seasons, gravitational force, scales, and light. In each category, the text is organized with 20 items about science concepts in astronomy, basic astronomy, and has 4-option multiple choice items. I have some examples. I have the example in Portuguese. I also have there if you want to take a look and give you some suggestions in English. In Portugal, in Portuguese curriculum, we have astronomy at the 3rd grade, the 7th grade, and the 10th grade. So the 3rd grade, the students are between 9 years old, 7th grade between 12 and 14, and the 10th grade between 16 or 17. So we have a validation of the test. It was made by 5 teachers of physics and chemistry, 1 university professor, 2 astronomers, 2 students from the 7th grade. They took 25 minutes to do it, and they gave us some suggestions. And 2 students from the 10th grade also took 20 minutes to do it. So the test was applied in different schools from our country. It was not intentional. Those schools were the teachers that wanted to participate and help us. We have 677 students from the 7th grade, 45 students from the 10th grade, and then 54 teachers, and those teachers were having training courses in astronomy. I have to be really quickly now because I have 5 minutes, and I want to show you what is really interesting. So we have here all the items. We analyze facility and discrimination. As you can see, we don't have 100% of facility. And we have the items 7, 9, 14, 17, and 18 that were very interesting to analyze. I hope I have time to analyze 2 or 3 of them here. So let's go back how we construct this test, this diagnostic test. So in category B, we have orbits and celestial bodies, astronomical objects. We took some misconceptions of the literature, and then we also took the items of those projects. Here's one example. This is the original one, and then we change it to the Portuguese curriculum, and we changed the image, as I told you before, to have more clarity and quality. This is the item, one of the items of the test. So the diagram shows that the path X, the Earth follows around the Sun, is nearly circular, while the diagram Y shows an elliptical orbit. The drawing is not to scale. So we have 2 images, and the students and teachers had to choose which one for them was the correct one. So as you can see, most of the students choose the option B. We have 58% for students from 7th grade, 63% from students from 10th grade, and 69% to teachers. We wanted to analyze this misconception again. So we put this question in the beginning of the test, and then we put another one, very similar, in the end of the test. So the number 17, of the following options, which is similar to Earth's path around the Sun? We can see the drawing is not in scale, and once again, we have the same data, and we analyzed that this data seems to reveal similar conclusions to the advancing science serving society in relation to the ideas exposed by students. So in these 2 items, we have 2 exceptions in the pattern observed in most of the tests, because in most of the tests, the knowledge of the students increase with the level of education. We have another one here. How much time do I have?
+5 for questions, so you can go into that.
Okay. Okay, thank you. So this is another interesting item. So the image represents the Earth and a satellite orbiting the Earth. Which of the diagrams best represents the force that Earth exerts on the satellite? So here we can analyze that students from the 7th grade, even they don't know how is the motion of the satellite around the Earth, 68% choose the option D, which is the right one. And so this is according to the literature. Another interesting item is this diagram below that represents stars and constellation in the sky as they were observed approximately at noon. So the sun is observed apparently near the star of the constellation Gemini. In what constellation is the sun be found on the sunset in the same day? So this is very interesting. If you analyze the results, 25% of the 7th grade students choose the option A, Gemini, which is the right one. But if you can see the numbers are very similar to the options 25, 22, 25. In the 10th grade students, you can see that most of them choose option C. So now we can say the difficulty they have to understand the apparent motion of the sun. And in teachers, we have some doubts, so they choose A and C. So the results were consistent across different schools and grades. So some misconceptions have a large frequency in different groups of students and even in teachers. We know the progress in knowledge with the level of indication in most of the tests increase. And another point that I wanted to say about why we choose the images is for enhancing the learning in astronomy. That's all. Thank you. I would like to say that this work was not possible with my professor that guided me with all of this. Thank you.
We have time for a couple questions. Carl?
Phil Sadler, I saw a talk by him on some more recent work, and actually they had pretty good evidence that if a teacher knew what the students' preconceptions were, that if they knew what they were, the students the teaching was a lot better. So that simply knowing what the students believed, somehow magically the teaching got a lot better. It really helped better learning.
If a teacher knows the misconception, they can deconstruct those misconceptions. But sometimes teachers have misconceptions too that they don't know they have. So they have to find out itself and deconstruct those misconceptions to be able to deconstruct all the kids' misconceptions. Okay. It's not a easy work to do. Yes.
Did the teachers get the results, like the answers to the questions, after they'd finished the questionnaire, so they had a chance to adjust their own misconceptions quite quickly?
No.
No?
It was anonymous.
But, I see, okay. So at any stage did they get to find out what those answers were? Like just as a group, like were they ever emailed out or anything?
I can ask them to do the test again and put the name on, and I will help them, but not for this one.
Other questions? Linda.
That's really great work. Thanks for sharing it. I guess I just thought I'd make the comment, building on what everybody else is saying, that even if you did give them the answers afterwards, like that's not good enough, right?
Yeah, you have to.
I think education research shows that you have to really confront people with this is something mentally has to shift. Like, oh, that's why that couldn't possibly be right. Not just tell them.
That's why, historical experience help with some of these questions to deconstruct. We have we can I can talk you about some books that are in schools, especially in Portuguese schools, that images that can make new conceptions on kids and so on. But if you are interested, I'll be here. I have my book, my master. You can read it. It's in Portuguese, but I can translate it. And I have the test in English if you want to, and help to make some changes, because we are always changing and validating the work and to get even better.
Thanks.
Very quick.
Very quick. Did the teachers know that you were examining misconceptions?
No.
Okay.
They had no reason to go and look up the answers after.
No.
Oh, sorry, are we online?
So I think we have to move on. And our next presentation is, let's see if I can get this right. Tibisai Sankat Singh Nava. How many? Yes? Okay, good. That I passed today.
Thank you.
And
How do I get there?
oh. And I'll give you the times for the 10 minutes, but there's also 5 minutes question and answer. So you can go into that if you need.
All right. I don't think I will.
Do you have over here?
That one.
This
No,
one?
one above.
Mhm.
No, go back. Sorry. The education of cultural astronomy.
Okay. You can switch here, maybe with this,
Space
these
bar?
arrows.
Okay.
No, with the arrows. Okay.
Arrows. Yes. Hello. My name is Tibisai Sankatsing Nava. I'm from Leiden University. I'm going to be talking about how to use cultural astronomy for education and whether this is an effective tool for education. Earlier this year, I started working with Tunawe and in Cape Town with the South African Astronomical Observatory and the Office of Astronomy for Development. And there I developed an educational module for Unawe about cultural astronomy. So I think everybody already knows what Unawe is, so I'm not going to go into that. Correct me if I'm wrong. All right. Unawe has an educational resource called Universe in a Box, which I assume you also know about. It's a hands-on educational kit with several modules about Earth, planets, the moon, solar system, and constellations. So we all know Unawe. It has aims for underprivileged children to educate and inspire them and incite a sense of global citizenship. So there's 5 modules, and what we wanted to do at Unawe is get an extra module, one about cultural astronomy, to kind of focus on the sense of global citizenship and at the same time educate children in astronomy. So why cultural astronomy? We already touched upon this a few times today. The first thing is the sense of global citizenship, tolerance for other cultures. Several people today already talked about this a little bit. But not just that. A lot of cultures around the world don't have access to science or to modern astronomy, but many of these cultures do have myths, traditions, things that are embedded in their culture which they are exposed to. And we can channel this, we can use this to introduce astronomy and other science by using these cultural stories. So then cultural astronomy would be a stepping stone to modern astronomy education. The activities that were developed were all inquiry-based, according to the guidelines of Unawe and AstroEdu, as Dilina spoke about today. So how did this go? There were several steps. First, of course, I did a lot of cultural astronomy research into the literature, spoke to cultural astronomers, to science communicators, looked into different stories from around the world to see which ones could be used for activities to teach astronomical topics. Then, after a short list and several reviews from different professionals, we got down to a few topics and started developing some activities. Once these were finalized, we went to the testing phase. This is very important, of course, because there are several activities being used with cultural astronomy, but it has never really been evaluated if it is useful or not, if it's effective or not. So that was an important part of the process. After the testing was the editing, so incorporating the information, the results from the tests. And then there was the Astro Edu submission. We all know what Astro Edu is now, from Tirina's talk. So the module has several activities, and they're of cultural astronomy topics from around the world. So there's actually a lot more cultures and countries than you can see here, but this is just to give an impression of, it's quite widespread. So the idea is that people from around the world will not only possibly be in touch with their own culture or a culture similar to their own, but also, a lot of different ones. You'll be able to compare and feel that sense of global citizenship. That is the hope. So this is what we tested. We tested whether it teaches astronomical concepts, whether you have that sense of global citizenship. So the question was, is cultural astronomy effective as a tool for astronomy education? And we defined this a little bit according to the domains of active learning from the UNAWE program evaluation guide. So we looked at several things, at the motivation that it gave the children, at the cognitive learning, the cultural awareness, and the scientific skills. And for this, we used several different tools. Child observations during the activities, we did this in the form of workshops. So during the workshops, several children were observed and everything was noted down. We also had a survey for the parents and teachers that were supervising the children, and also a learning assessment, a direct pre-test, post-test learning assessment, nothing long-term, but still quite clear. The testing was done in South Africa, at SciFest Africa in Grahamstown earlier this year, and also in Cape Town through the outreach of the South African Astronomical Observatory. So in total, we had 161 children, 18 parents and teacher surveys, and 4 children were observed throughout the entire time of the workshop, just for some extra information. Oh, here you see some pictures of the different times that the tests were done. So the results, it was actually quite positive. The children were very engaged, very motivated, and the teachers and parents were very excited. From the direct learning, it was clear that in any case, the cultural stories related to astronomy stuck with the children. They remembered them, and they also remembered why this was an introduction to specific topics. And they also displayed knowledge of astronomy-related knowledge that was introduced by these questions. So that was nice to see. And then from the observations, the children participated actively. They worked in teams, which are specific objectives of the UNAWE program evaluation guide. But not just that, we also listened to their conversations, obviously, while they were working. And one of the first introductory activities for the little ones is just talking about what is a star, what does it look like, what shape does it have. And after having this conversation, I asked the children again to draw some stars. And it was this very little girl who said to her maybe brother, older boy, you don't only have to draw stars with 5 points, because stars are not pointy, remember? And things like that is very nice to see when you've been talking about this, that even the little ones still grasp it and can share with their peers. That was very nice. And then there was another time, I'm just giving another example. We showed them an artist's impression of the Milky Way, talking about what is a galaxy, things like that. And one boy asks, whoa, who took this picture? They must have gone very far away. Which is nice, because they're paying attention, and that started that conversation of what is an artist's impression, how far have we been, things like that. So it was very interesting. And those things show that the children were engaged, they were paying attention, and they were actually learning things, so that was good. In general, there were quite successful workshops. Everybody seemed quite happy during and afterwards. The children and parents asked astronomy-related questions in every session, so it's clear that the cultural astronomy, in any case, brought the real astronomy to the forefront. The children participated actively, and like I said, positive feedback. It was great. Everyone was very interested in using these activities in the future. So there were some challenges. It was in South Africa at SciFest Africa, where you have different ages, you have children with different backgrounds, children who are going to high school, but also 7-year-old kids who barely speak any English. So it was very challenging to run a workshop like that, but also very interesting, and we adapted the resources accordingly, so it's layered depending on, it's specific for ages, but also a little bit layered depending on the audience. There was no long-term learning assessment. As I said, we just did the pre-test, post-test, although yeah, there was no other possibility, of course. And it's a relatively small sample size, especially with the child observations, but we think it does give a representation of what is possible. And in the future, if we want to know more, we should just try it with a larger sample. So just to give you an idea of the types of activities that were part, this was in the outreach center at the South African Astronomical Observatory. These are Club Scouts. After they drew their stars, they presented their own cultural story. It was very nice. This is the end of the workshop. So I'll just show you one activity. This is actually a card game about meteors, meteorites, comets, and it's about the difference between the different types. So first, this is for a little bit older children. They get a fact sheet with information. Then they get the bottom cards, which are the characteristics cards, and they have to fill them in for each type of space rock. And what happens is we have different story cards with stories from all over the world. So I'll show you. This one, for example, is from Romania, and it's a story about a bright dragon that flies through the sky quickly and comes back often. So the children will read this story and then have to pair it to one of the, so is it a comet? No, because it comes by really quickly, so it must be a meteorite, oh, things like this. So it's a card game. We played it with several kids and they had fun. And they seem to remember everything afterwards, so that's good. But anyway, just to give you an idea of the activities. Here it's matched. So in conclusion, cultural astronomy seemed to have worked well with the activities that were tested. The participants were motivated, they displayed cognitive learning through the different tests that we did, and they also showed awareness of different cultures. So that was great. Future research should definitely focus on bigger groups and not just South African children, of course, but I think it gives a good indication that cultural astronomy can be an effective tool for astronomy education and inspire global tolerance. So, you know, they're going to be available soon, hopefully, so I invite you all to use them. And also, we're all from different places, so I think we can also come up with our own things that we can then share with each other and keep the cultural astronomy going, and thereby do astronomy and that good sense of tolerance. That was it.
Okay, that's great. That's very interesting. Questions?
I guess it was
No
very
questions?
clear.
How long did you spend in South Africa?
3 months.
Okay, I think, did you say that in your talk? I must have missed it,
Ooh,
sorry.
no, I don't think so, no.
Okay, so that was, how did you like the country, and how easy was it to get used to living in a different place?
I absolutely loved it.
Wonderful, okay.
Yes.
I think this is a wonderful project, and I applaud you for actually going there and carrying it out. Very
Thank you.
good.
Thanks.
Well, I have a question too. It's related, I guess, because my interest is in sharing. I've always been interested in the idea of sharing cultural astronomy between different cultures as a way to connect each other too. Do you have any thoughts on that? How would this translate, or do you think that that this could be applied in a way of sharing cultures with each other? Do you have any insights on that?
Definitely. It did occur to me, or I did notice that a lot of children don't know their own cultural stories at all. So to that extent, some were surprised, but then they started noticing similarities with, for example, South American culture. So the South African kids would listen to a story, I mean, I did it on purpose, of course, in the resources, but there would be a South African story that somehow was quite similar to a South American one. So then people started looking at it and noticing that maybe they're not as different as they thought at first.
Exactly.
Yeah.
That's great. Any other questions? Okay.
Thank you.
Very good. Thank you. Okay, well, next we'll have Linda Struve talking about her experience in Nigeria, another interesting culture.
Yep.
Where is your presentation? This one? Internet, yes.
Okay. I can like this. Great. Okay, hi everybody. Thank you very much for being here, and thank you to the organizers for having me. My name is Linda Stribba, and I'm a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics in Toronto, in Canada. And what I would like to tell you about today is work that I've been doing with a group in Nigeria. So we've been having a lot of really great talks so far. Many of them are about kind of big picture programs that are kind of worldwide. I'm going to tell you about something that's sort of a specific example, so you can learn more about what's going on in Nigeria and in West Africa, and also to give you an example, just kind of in the trenches, about teaching inquiry and using results of education research for developing activities and evaluating them. Last year in October, we held the first West African International Summer School for Young Astronomers. We had about 70 undergraduate students and some teachers from around Nigeria and Ghana attend. You can visit one of these websites, astronomynigeria.com or sharetheuniverse.org, to learn more about the program. I'm assuming that most of you have never been to Nigeria, so let me give you a bit of an introduction to the country. Nigeria, I guess I don't have a pointer, but Nigeria is in West Africa. It's kind of colored red on the side there. It's one of the largest countries in Africa. It has almost 200 million people and has the largest economy. Its capital city is Abuja, which is in the center, and you've probably heard about the awful sectarian violence that's going on related to Boko Haram. While we were there, we felt quite safe, and I'm not going to go more into that aspect, but you can ask me about it later if you're interested. Nigeria has a low United Nations Human Development Index, which you probably know is a measure of education level, life expectancy, and per capita GDP. The mean number of years of schooling for adults there is only 5 years, but the situation is improving, and a student that enters school today has an expected number of years in school of 9 years. There are a couple of dozen universities around the country, only one of which has astronomy. And Nigeria, however, is quite interested actually in developing astronomy for a couple of reasons. The Square Kilometre Array in South Africa is of great interest to Nigeria. They'd like to be involved in that. There are some radio dishes that are in part of the country that were put there for telecommunications by other countries many decades ago that they're now converting into radio telescopes. And Nigeria has 2 satellites of their own that they're using for remote sensing, and they have kind of space travel ambitions. So the government is interested in putting resources towards astronomy education. And so, actually, I was also going to mention that they speak English in Nigeria because it's a former British colony, so that helps for our ability to communicate easily with people there. So the Nigerian government is interested in putting resources toward this, and so my colleague Mike Reed and I from Canada, we met this astronomer Bonaventure Okere, he's shown in the top left there, at the IAU General Assembly meeting in Beijing in 2012, and devised the plan of holding a summer school for people from around the West African region. These are different collaborators that were part of the program. We had two other Nigerian astronomers that were part of the program. One is shown here in the middle, Daniel Oko. We had a collaborator in California named Lisa Hunter, and then this is a picture of me with Daniel and the 3 graduate students from the University of Toronto. And I led the team where we developed the whole curriculum of what we taught and the teaching and the evaluation, working with these graduate students. So the goals for the summer school, kind of in the biggest picture sense, were to introduce West African students to astronomy to a level that they'd be able to keep going out and learning more about it on their own after the school is over. To exchange ideas about teaching and learning in West Africa and North America, and to build a foundation for a sustained astronomy partnership between West Africa and Canada. In developing our curriculum towards those goals, it was really important to us to incorporate results of science education research in order to develop as effective a plan as we could. two really important aspects we wanted to incorporate are that we would teach scientific thinking and not just content, as many of you have been talking about in the programs that you're doing as well, and to make sure that we incorporated assessment to evaluate our teaching along the way and everything that we developed. So the teaching activities we developed overall were an inquiry-based activity on the cosmic distance ladder. That was kind of the centerpiece, and I'll tell you more about that in a moment. We had interactive lectures and problem sets. We had group discussions on topics like why should we study astronomy, and solar observing, and a hands-on lab about the sun. And this is just a photo of students using sunspotter telescopes to observe the sun and measure the sun's rotation. The centerpiece of our curriculum was this inquiry-based activity on the cosmic distance ladder, so I'd like to tell you a bit more about it. The overall goals that we had were, first, that students would learn about the scales in the universe, which is kind of an amazing, inspirational thing, as many of you have already talked about. The content was to understand and be able to apply the parallax method for measuring distances and the inverse square law for measuring distances. And then maybe most important of all was the scientific thinking goal of having students learn how to go from a question to figuring out something, a question that they had, to figuring out something on their own. So the way that we had them do that was we gave students a whole bunch of images of different astronomical objects and encouraged them to ask their own questions about those images. Then they broke into small groups where they investigated the answers to those questions on their own, and then finally joined into different groups where they discussed what the results of their investigations were. So I can take you through a sample inquiry path. Based on this image, a variety of students wondered, what are sunspots? And so a little bit of background about our students' experiences with learning and education so far. Our students are very used to formal education, formal lecture, maybe not even any questions during the lecture. I mean, I've seen this in my home country in the United States, but it was even much more so in Nigeria to what I saw. But our students were extremely inquisitive. They had tons of questions about everything and were really excited to ask things, but they didn't know what to do. They didn't feel that they had any idea kind of how to proceed. They were happy to ask the questions, but didn't know what to do forward from there. So we kind of tried to give them some nudges and guidance by asking them things like, well, what observations would you want to start answering this question of what sunspots are? And groups came to the idea, okay, well, how big are sunspots? That would be a way of characterizing them to start understanding them more. And they had this image, so they measured the size of the sunspot relative to the whole size of the sun. They said, okay, great, now we know the size of the sunspot. Then we said, well, but how do you know the size of the sun? They said, well, we were taught it. And then we kind of pushed them and said, well, but what if it's not right? Or what if, okay, you have this question, but what if you have some other question that nobody in the world knows the answer to? What are you going to do then? And this was kind of, it felt like the transformative kind of aha moment for our students, like, wow, I shouldn't just believe everything that my teachers tell me or that I read in a book, and maybe I have the ability to figure out some of these answers on my own. I don't just have to look to somebody else to tell me the answer. So it was great, and our students gave us really positive feedback. Like one student said, this process has actually made me realize that I can think and find answers to questions on my own without external help. I can now say I can think like a scientist, which obviously made us very happy, and many of our students said other similar things as well. In my remaining couple of minutes, I'd just like to talk about how we evaluated the school. Okay, 1 minute. We gave, is it okay? Okay. So it was important to us to evaluate the school, and so a couple of different ways that we did it were through surveys. So we gave students surveys before the school, after the school, and then 6 months after the school to measure their learning and a couple of other things. So we used astronomy concept inventory questions, which have kind of come up in some of the previous talks, although maybe not with that exact name. So these are questions that have been validated by many, many, many groups of hundreds of students to make sure that they really ask, and the kind of responses that you get are the things that you think you're asking. So those are used in education research. So we gave questions like that to our students. And we found that they had substantial improvement on some of the things, like distance, that we had time to spend a lot of time on, and not as much on other things. We asked them about their interest in a career as a scientist and their confidence in their ability to act and do things like a scientist. And we found that that started out very high and remained high through the school. And we also solicited written and oral reflections on the school overall, on the inquiry activity, and every day. And I shared one with you, and I'll share a couple more with you in a second. So for the future, we're writing up the activities that we did for AstroEdu. So hopefully in the near future, you'll be able to check them out and use them too if you're interested. We have a Facebook group where we're kind of keeping the community of students together, and we're trying to turn it into a forum where graduate students at the University of Toronto will come in sort of for a week. They'll host and share what their research is and have a discussion with students, also discuss career possibilities and just anything of interest. We had 2 alumni that were going to visit Toronto this year, 2 alumni from the school, one for the International Astronautical Congress, which will take place in Toronto at the end of this month, and another who was coming for an instrumentation summer school at the University of Toronto. But both of these students had their visas denied. And I don't know if this is an issue that any of you have run into. It was pretty disheartening for us, and if you have any thoughts about how we can get past this to get a real actual exchange, I would love to have your thoughts on it. And finally, we've been preparing to hold the school again. We'd like to make it an annual thing in October of this year. We got some OAD funding for it. But the Ebola outbreak has caused us to postpone the school. So we're waiting until that's contained, and hopefully early next year we'll be able to hold the school for a second time. So I will just end by leaving you up with some more quotations from our students. This is some of what's going on in Nigeria. This is some thoughts on how inquiry can actually work in the field, and I'd love to have your questions. Thank you very much.
There's time for questions. Rosa.
I have a question. I mean, this is a challenging work to be done. Would you be willing to go to other countries in the neighborhood or bring teachers from the neighborhood to train them? And also, can inquiry be easily implemented in schools in those countries, or at least from your experience, was that not a challenge?
Yes, it was a challenge. I guess to answer your first part of your question, yes, I and we would love to go to other countries in the area. We'd love to train teachers in this. This was kind of a first foray into it, but we'd love to do lots more. Yes, teaching inquiry is difficult. I mean, it took a large mental shift for our undergraduate science students here. I mean, those of us that participated in designing this, we were part of a program for graduate students and postdocs to learn about inquiry-based teaching. That's where my background in this is. I've done that for 4 years. That's a huge mental transformation for me thinking about teaching, and I'm a scientist. So implementing it in the classroom is hard, but I also think it's critically important because that's where you actually learn to think like a scientist. It's not when somebody tells you how to think like a scientist. It's when you have a question you're interested in and you have to work with other people to figure out the answer to it. So I'd love to be able to hold workshops like this where we give this kind of inquiry experience to teachers and then help them figure out how they can implement it in their classroom, definitely.
So I'll just make a comment and see your thoughts too. And one project we have under Astronomers Without Borders, it will be tomorrow's Telescopes of Tanzania, and they have done in conjunction with Rosa and GTTP some training of teachers in this type of thing. There's 2 different approaches, and these are for the younger kids. But what do you think? Can this be directly done to the students, or do we have to change things within the classroom? It's a change in culture, basically.
Yes, it is a changing culture. I think you have to change the culture in the classroom, but I don't think you need to change like necessarily sort of physical things within the classroom. Yeah, I think we can definitely do a lot with this.
Okay.
What was the rest of your question?
Yeah, it wasn't. I guess it was as much a comment as a question. So
yeah.
You'll be interested in this tomorrow.
Yeah, definitely. And we're going to talk more about inquiry at the AstroEdu workshop this afternoon. So I hope you'll come to that too and think more about this. Thank you.
Okay, next we have something interesting. Dominguez Barbosa, Music of the Spheres, Whispers of the Universe, Human Sounds. A performance. This is not a switcher, a video switcher up here or something. This is a keyboard. What do you want me to do?
Just hold it. I'm going to switch. Yes, the other side. Sim, eu provavelmente baixo aqui o microfone, deve ser suficiente. Senão vai descalibrar tudo outra vez ali com a peça. Pronto, a peça tem alguns subias, etc. Se começarmos a mudar para aqui, depois eles podem saturar. Tem 15 minutos. O despacho em si. Está difícil? Uma peça que foi planeada pelas técnicas de som envolvidas. Não está a entrar? Posso, desde que vocês tenham o software de vídeos e som. Os têm ficheiros that is a dot with WAV files and MPEG and flash files. Ele não consegue. A peça vai sair daquele ali. A peça a seguir. Mas eu aqui faço com o microfone. Baixo só o microfone. Ah, ok. Olha, é a primeira vez que vocês não têm HDMI.
Não, isso é HDMI. Qual é o problema do som?
No princípio. Não, é um PowerPoint que tem alguns ficheiros de vídeo e sons.
Just a sec, we're having some technical problems here.
Posso tentar passar a ver se dá.
Esta ficha,
Sim, sim.
este rebordo é muito pequenino.
Vocês têm flash e lê MPG. MPEG.
Sim, é excelente. Fazer ver os drives, não, MPEG de vídeo.
Já se vê? E também é difícil de
Também é difícil
fazer
entrar
download.
aqui.
O que aconteceu aí?
É um perna que está.
É isto, não, é a parte do corpo, fica no meio do perna.
Se calhar temos que trocar esse cabo para mim.
E aqui não dá nesse jeitinho.
So while we wait for the technical solution to come, I urge you please bring your presentations in pen drive so we don't have to shift computers. This is always an issue, okay? Please bring your presentations to us so we can upload to one computer only.
Acho que alguém conseguiu enfiar aquilo neste PC, só que agora depois tirares não consegue.
Quer tentar no outro computador?
Tem que ser com jeito.
Não.
Este cabo é daqui, imagina da sala. E este tipo de coisa já
Olha,
estava
e se eu pegar um cabo do meu data show e ligar a esse? E
Não, porque tem que ser mais fêmea.
pois, exato.
Estes cabos
Não
são
tem uma
mais
extensão? A extensão deve ser assim, não servirá?
Só se for o mais fêmea. Porque os cabos eles
Se é
são
uma
todos
extensão, deverá
mais.
servir, não?
Ok, vai, está aí. Tá.
Ele a partir do momento que entra.
Falta esta parte aqui, rentabilidade não
Eu vou
deixa
buscar,
entrar.
Depois experimente lá o outro computador.
Vamos experimentar agora o outro. Está alto? Vou trazerem outro computador, se tiver uma entrada um bocadinho mais larga.
Presta-me a chave aí Sim, esta é mais folgada. Aqui entra bem, certeza. Mas pronto. Aqui entra bem.
Será que entra agora, aqui com esse jeitinho? Já vimos que aí entra.
Não, ali entra.
Pelo menos aqui.
Este entra. Mas é mais.
Não é não.
Não, mas ele neste já entra.
Já entra.
Aqui é muito apertado.
Esse aqui é mais fêmea ou é mais
Não, é mais.
Bom, vamos ter que passar por aí.
E agora é não tirar se alguém trouxer o próprio computador?
O PowerPoint é que é 2010 ou...
É o Windows 8, é o último.
Tem de ser 2010 então.
Sim, quando eles reinventarem outro tipo de ligações, isto é de pinos foi a pior porcaria que eles fizeram.
Não, porque nós até já costumamos usar com projetores HDMI e
acabou.
Não há pinos.
Os pinos, não fica assim. Vou ver desse lado. E trasladamos o material para aqui. Já está aí. É assim ou ao contrário?
Ela é USB, mas também tem.
É assim.
Não sei se será assim ou se será para cima.
Para baixo. Ai, mas não prende? Mas deve ter, vamos ver.
Ok. Vamos lá ver se dá.
Seja MPEG. Se quiser tentar, seja MPEG antes.
Para o som já vai sair. Ok.
Ele sai direto, já não sei se reparou, estava a sair já para
Okay. Hello, everybody. I'm sorry for these small technical problems, but we can give you musics and sounds. It's not very good for dancing, but it's very good for listening. Was an exercise collaboration between scientists and artists. I just sat in front of a computer trying to explain what the Big Bang was and what acoustic waves in the universe are, and what similarities with acoustic waves made by humans, in particular when they have some harmony and that we call music. So at the end of my very brief talk, you listen to electronics music piece by my colleague Isabel da Rocha, which is a young composer. And the piece will just end by the Goldberg variations of Bach to clean your ears. So what it's all about. So I'm just describing what we think, what are whispers of the universe and human sounds. And essentially, what I'm going to talk about is that we need very big ears, like radio telescopes and antennas. And this is just an artist snapshot of the square kilometer array. And if you plug in a sound card into your receiver, you can transform some radio noise into sound noise or sound musics, and actually take that as fabric to music. In a sense, the universe is full of acoustic waves. Believe it. They don't propagate very much because the universe is very empty, but there is some matter, very low density matter. So acoustic waves actually do propagate. And electromagnetic phenomena also interact with matter. They create plasma waves and they create radio sounds that you can listen into normal radios. In fact, that's a phenomenon that was well noticed by Edison and also by Jansky, for example. So this harmony of the spheres actually means that acoustic waves in the universe have some preferred modes. For example, if you take your drums, what is the drum all about? The sound you listen is just an acoustic wave that crosses the membrane of the drum and creates a pressure wave that goes straight to your ears. And what you listen is something like this. Okay? If you hit the drum, then you have a superposition of another mode, and another mode, and yet another mode. You have many modes crossing. So your vibration to the drum has plenty of modes. The combination of some of these modes is a note. Okay. So if in instrumental music, you select and a few notes. Basically, you're selecting some vibration modes over the others. Okay. So what about the stars? Well, the stars also vibrate. And for example,
this sequence shows an animation of exaggerated displacements of the sun's surface produced by the 5-minute oscillations.
So you notice what it is. So it's just a YouTube video, but it just shows acoustic waves in the surface. Every star oscillates and is the field of the study of what we call now astroseismology. It's just acoustic waves. And what you're seeing that is that by studying that acoustic waves, you can decompose these sounds, stellar sounds, into modes, and you can listen them. For example, You also notice that the planets start interactions. So if you take your sun, which is out there at 8 light minutes, well, sometimes you have plasma waves coming from the sun. And so they interact with the Earth. And if you have the proper radio telescopes, you can listen to that. Okay? So that's what we call aurora. And of course, so that's what an aurora borealis is heard by a radio telescope. And sometimes you just plug in, if you are in the Arctic, you just plug your own radio receiver, and it's very easy to listen. Okay? So what about more planet interactions? So we have found out with space missions that all the planets actually have magnetospheres, in particular Jupiter and Saturn, and you can listen to the aurora. And actually it's very, very interesting because we are in a planetary science conference, and this is just Saturn aurora, listened by Cassini. These sound files are available at NASA websites. You can just plug them in. But Isabel will show how Uranus, Neptune, Saturn can be combined together and show you how the universe looks like acoustically. Okay. So there is something that I cannot pass. Okay. So this is another sound, which is better. So you see the aurora in Saturn, okay, as seen by the Hubble Space Telescope. And you direct your own telescope, you hear the previous sounds. Okay, so you can put your own visual or set of images from the Hubble with the set of play music from Cassini. The fundamental modes that fill the universe are what we call the cosmic microwave background radiation. And the cosmic microwave background radiation is just a fossil of the early universe. It just tells you that the universe was very hot, very dense, so it was a fluid that is expanding. Have you ever listened to an expanding fluid? It's a balloon, for example, a piston that empties. So it passes from acute to very grave sound, okay? From soprano to a baritone. So you're going to listen to the cosmic microwave background sounds. And these sounds, you'll hint that what you're listening is just the infancy of the universe, just a crying baby, basically. And of course, the baby is just growing, so it stops crying, fortunately. And then you can pass from a well-tempered clavier to a well-tempered electronics, from Bach to Laurie Spiegel. You know who Laurie Spiegel is? Not at all. So I'm just inviting Isabel to tell who Laurie Spiegel is, because Laurie Spiegel is the only Western artist whose music is featured in the Golden Records aboard the Voyager. She was a pioneer of electronics music back in the 60s and the 70s. She worked at the Bell Labs. She was very much influenced by the telecom noises, the radio noises, etc. So she just started to pioneer many techniques that later composers, have you heard about Vangelis, for example, etc., used. So at this stage, I'll just tell you that this is a very nice educational material that can be very easily being explored and implemented with small radio telescopes. And I think Rosa will found this very interesting because it's just plug in a sound card into the antenna. Okay, so I'm calling my colleagues. It's their show, so I hope you enjoy, and be patient for the first 5 minutes.
Colocar o cabo de volta. Vamos ter que o tirar. Esse, por aqui. Não, isso não é preciso ter, a não ser que queiram tirar o computador.
Sim, não é preciso. Não vamos ter problemas de cabo.
Ok. Seja melhor falar do lado espiga, onde disse que eu ia falar.
Sim, sim. Escreva assim o seu trabalho. So, while she assembles the piece, she will tell us about the techniques she employed in this work, and then they will have the Bach, and then we'll have the Bach performance by Melissa Fontoura, which is a professional pianist, and she was very kind to come to us and enlighten this work and my presentation with this.
Hello, good afternoon. Thank you very much for your attention. Thank you for this opportunity. Melissa and I are very happy to perform here. So our piece will be part electronics, which is my part. It's an electroacoustic piece, which also had a bit of programming with Max MSP, but you'll hear the final product. And then Melissa will play the aria from the Goldberg Variations from Johann Sebastian Bach. And this piece has two parts. A part which is kind of scientific. I tried to make a sound version of the cosmic background radiation based on the work of Mark Whittle, an astronomer from the United States. But it's kind of, well, homemade. And then I used recordings from planets, from NASA files. And I tried to do a subjective product which has a kind of a philosophical meaning which represents the birth of the universe, but also in existential terms, the birth of a new life in ourselves. Some people can call it a life crisis, turning points in our lives where we no longer can exist in a certain way, and a very big change occurs in ourselves. And this change is represented by a beating heart. Talking about Laurie Spiegel, she's a hero for me. She's an American composer, and like myself, she is half a kind of a scientist because she programs. She has created many programs for computers. I'm part scientist. My grandfather was a surgeon, and so I ended up studying biology before becoming a composer. And I worked many years as a researcher for Porto University. And now my scientific research is in acoustics. I work in the acoustics lab for ESMAI. And so Laurie Spiegel, she's half a programmer and half a composer. And funny enough, she was the only living composer chosen to be a part of the Golden Record. All male composers in the Golden Record are dead, like Beethoven, and she was the only living composer at the time chosen, funny enough, a woman, which is very rare. And what she did, she tried to create a sound version of Kepler's Harmonices Mundi, because Kepler studied the work of Pythagoras and he did a theory of himself as to the acoustical proportions of the universe. And so she created an electronic piece which can be heard in the Golden Record, not in the music section, but in the section of the sounds of the earth. So my piece was also a bit based on Laurie Spiegel's work. Well, I think that is enough. We want to hear music, so we hope that you enjoy our piece.
We are almost a half an hour over now. We have 5 minutes left in the coffee break. I don't know if there's any coffee to be had, so if you have any questions or comments, please bring them to the presenters directly.
So let's thank all the presenters of this afternoon, and Domingos and the fabulous artists are going to be with us for a few more moments at least. We have no coffee break time. You just go outside, drink your coffee and come back, okay? You have 5 minutes to go and come back. Go! Mas puseste aqui a apresentação? Já está. Não puseste? Sim, então tu apresentaste a partir daqui ou não? Ah, fizeste aqui. Sim, por favor, Domingos.
Yes, teacher.
Não há como. Fez shopping no hoje de manhã. Olha o instrumento.
Ah, é? Então. Sim. Eu estava só aqui a.
Parabéns, amigos. Parabéns. Muito bom.
Eu não vou usar, eu só quero o projetor. Não está a precisar, para não.
Ele está temperamental.